Thank you very much, Greg, again, for the introduction. I will be brief, and I will show you some results again. So I'm not sort of directly writing this code, but there are people who are. And this is our collaboration with Bill Tang and Bei Wang in Princeton University. They're not here, but they contributed as much as they could remotely. The goal of the project was pretty much simple. So MS Flux, in its most advanced version, solves the Boltzmann kinetic equation coupled with MHD equations for plasma, but we solve neutral, the transport of neutral particles kinetically. We solve MHD equations coupled with the Boltzmann equation. So, and we use the Monte Carlo method to solve the Boltzmann equation. And the reason we are solving, in principle, the Boltzmann equation is that the mean-free path for charge exchange between hydrogen atoms and protons can really be very large. So the smallest is probably of about 50 astronomical units, but it can be 100 in different regions, 200, so pretty large. So, and the computational box can be also very large. As I told you yesterday, it can be 20,000 astronomical units. But in reality, this is not what is important here. The distance from the Sun to the heliospheric termination shock is 100 astronomical units. At the width of the compressed region between the heliopause and the heliospheric termination shock is about 35 astronomical units. So there's no way we can solve this, with equations of fluid dynamics, and that's why we are using Boltzmann equation. Charge exchange, actually, apart, of course, from solving the Boltzmann equation, which gives us the distribution function, but of neutrals. There is an issue related to the source term on the Boltzmann, on the MHD equation. The source terms are determined actually from Monte Carlo simulations of neutrals. So then ideally we should use the obtained distribution function and feed it into the source term. Source terms are actually calculated in the Monte Carlo module and then provided to the MHD module. And these modules are sort of independent. We perform iterations. And the nature of Monte Carlo simulation is such that doing time-dependent simulation is a little bit complicated, but possible, because in order to do time-dependent simulations, we must, of course, use very small time step. But in this case, we should have enormous number of particles which propagate through the computational region. Practically, maybe excessively large. So otherwise, we can use smaller number of particles, but perform several implementations of the same thing, okay, to obtain smoother source terms. So the idea for this reason, I show right here, actually, in the figures, I show the trajectories of the particles, and each time particle moves, of course, a neutral atom moves along a straight line, but each time charge exchange occurs, it just starts moving in some different direction, depending on the properties of the plasma in this point. Okay, and the probability of calculation, of course, is also determined somehow. So the idea was that since the kinetic module takes longer time for simulation, we decided to optimize it by using GPUs. And this was the essence of our collaboration. So I will show you here the performance results Right here, you will see that CPU simulations, we use actually OpenMP hybrid parallelization strategy. Within the node, it's OpenMP, but among the nodes, it's MPI. And so for different threads, and there's two main subroutines here, the move subroutine, which actually propagates the particle. But there is another extraordinarily important subroutine, which is called split. Anybody who is doing Monte Carlo knows about that, and especially for this kind of problem, where the sun is tiny, and we inject particles at a sphere of fewer thousand of astronomical units. The probability of a neutral atom actually to have a trajectory close to the sun is very low. So we actually split and merge particles. And so there are major subroutines here, move and split. And you can see here that indeed what we succeeded in visible acceleration on for these subroutines on using GPUs. So in other words, speed up right here for this subroutine is 40 times, and for this one 33 times. Well, it's not like this is the final results, unfortunately, because there are issues still which were not, which are being taken care of right now in the code. It's mostly because the analytic plasma profile was used for these testing purposes, and and in principle we should read data files from should read from a data file and then distribute among the nodes. So, and this was not actually done or finished. It's the work in progress. But anyway, the average comparison here, compared with the CPU code which runs on a single socket of Bluewater's XK7. Now, the GPU version gives us 18 times acceleration, which in principle, of course, if this remains after these additional changes, which I promised we still need to do, so these, of course, will be very happy about this result. So there are some details, of course, here. We tried to use OpenACC and failed. There were issues or combination of the current version of compilers, PGI compiler and OpenACC. We waited until the new version arrived, and but while we waited, we actually GPU version, CUDA version was implemented, and so the results which I showed previously here so were obtained with CUDA. So we created, for all team members have access to these files, and we both together on the Princeton side and on our side at UIH, we are now implementing these read-write options, which will not actually, they should not affect the productivity of the code, but they are simply to make the code realistic. Because the idea that Bei Wang is now running a standalone code, but we need to insert it back into MS Flux. So for this reason, of course, all functionalities should be preserved across standalone and the real code. And we are working right now on that. We acknowledge the help of the IME accelerator team, Van May, who actually helped a lot. NVIDIA people collaborated with Bei Wang a lot. This helped her, so rewriting the kinetic model. So now the current status, we are porting the optimized and revised GPU version into only of the kinetic module, I emphasize here, into the production code. Once the result will be available and we check that it all works, this will be the end of the project. And this is my last slide. Thank you very much for your attention.